The quadriceps is made of 4 different muscles: the rectus femoris, the vastus lateralis, the vastus intermedius, and the vastus medialis. The rectus femoris is the main muscle supported by the 3 other muscles. It's located at the front. When contracted, your quadriceps serve 2 main functions: hip flexion and knee extension. Hip flexion is essentially just bringing your knee closer to your chest, which is very important in running, while knee extension is one of the main components to generate power while kicking a ball. The quadriceps is composed of 4 different muscles that sit at the top and front of your upper leg. The rectus femoris is a bit different as its origin of location is at the pelvis, and it inserts around the patella into the common tendon group into the nose of the tibia. All of this is being done on top of the 2 vastus muscles in the middle of the quadriceps. The vastus medialis, one of the 4 muscles in the quadriceps, its primary role is to extend the knee joint while also stabilizing the kneecap during movement. It's located on the inner side of the thigh. The origin of its name is Latin, vastus meaning great or large, medialis indicating that it's on the inner side of the thigh. The muscle's origin is from the medial lip of the linea aspera and the intertrochanteric line of the femur, essentially high on the femur. Vastus medialis is then inserted via the quadriceps femoris tendon, which is then directly attached to the nose of the tibia. The vastus lateralis originates from the trochanter and the lateral lip of the linea aspera of the femur. It inserts onto the patella via the quadriceps femoris tendon, which is then attached to the nose of the tibia. All of these muscles work with your patella, which is just your kneecap. Your kneecap's function is to help muscles and tendons work correctly. When your quadriceps are contracted, they allow your leg to be lifted up. Your vastus muscles aid in bending your knee and lifting it back up. The vastus intermedius is located in the anterior compartment of the thigh, and is also inserted via the quadriceps tendon onto the patella to the nose of the tibia. It is found in between the 2 other vastus muscles and also helps in knee extension and stabilization. In the diagram you can see that it lies below the rectus femoris.
Let's talk about levers. The way your quadricep lifts your foot when you move your calf happens to be a 3rd-class lever, as shown by this diagram. This means that the effort is placed between the fulcrum and the load, requiring the most force to lift the load. However, because this is a problem of mechanical advantage, it is not without its virtues. This means that it is much easier to move the load faster. This is great for kicking things, like balls, but not so great for lifting heavy objects, especially not slowly and carefully. This makes it the perfect muscle for kickball, which is our sport. Let's take a look at the physics. In a 3rd-class lever, more force will need to be applied by the effort than in a 1st or 2nd-class lever. This is because the rotational equivalent of force is torque, which is force times radius, which, in this case, is the distance from the fulcrum. Since the load is also applying a force in the opposite direction, this needs to be counteracted by even more force, which would mean an equal and opposite torque, from the effort. This is a way for us to apply more force in a shorter amount of time, which is important for kicking, because we want the ball to go fast, and we can't just apply a force in a certain direction of a certain magnitude instantaneously. But because the effort is conveniently close to the fulcrum, things are less problematic. By finding the ball's initial velocity after being kicked, we can calculate how much energy, via torque, was put into the system by my quadricep. We measured my calf to be about 21 inches, the ball to be 1 pound, and the rest of my leg to be 12.2 pounds. In metric units, that's 55.9 centimeters or 0.559 meters, 0.454 kilograms, and 5.53 kilograms, respectively. Based on the slow motion video we took, we calculated that the initial velocity of the ball was 7.14 meters per second. We got this number by finding when the ball was 1 meter away, and then taking the difference in time between that distance in the video. Next, we multiplied it by 8 because the slow motion was slowed to 0.125 times speed. This slow motion helped us get a more precise measurement because we have a lot more frames to work with in a shorter amount of time. Now we need to figure out the moment of inertia of my leg, which is basically rotational mass. For each individual particle of mass, it's mr squared. But we are not dealing with point masses. The moment of inertia for a rod is 1/3 mr squared. So, if we calculate all of these values, the moment of inertia for my leg is 0.575 kilogram meters squared. This means that if we want to accelerate the ball from rest to a certain velocity, we could use conservation of energy to figure out how fast my leg was going when it collided with the ball. Based on these calculations, it can be concluded that my leg was going 9.42 meters per second when it collided with the ball.